Hello, folks. Welcome to Microsoft Build 2017. My name is Sam. Okay. Okay. Hello, folks. Welcome to Microsoft Build 2017. My name is Sam.
My name is Michael.
And today we are here to talk to you about actualizing a Lambda architecture to build out a fleet monitoring solution on Azure. Now, some of you all might be wondering what a Lambda architecture is. If you think of the Greek letter lambda, it's one line splitting into two, as you see on your screen. One of these two lines represents the hot path, and the other one represents the cold path. On the hot path, you can ask questions on data in motion, and using the same consistent scheme, also go ahead and ask questions on data at rest. Now, asking questions on data in motion enables you to unlock insights that might be perishable and valuable only during a certain window of time. It is also true that nowadays decision latency and the time to insight is getting more important than ever before. And the streaming path that we call the hot path here enables you to unlock those insights. Correspondingly, there is also the ability to ask questions on data at rest that enables you to ask powerful questions on a very large corpus of data, thereby enabling you to get answers in a scenario where response times to get the answer might not be super critical. So this is what we have in terms of a Lambda architecture, a consistent mechanism to ask questions on both data in motion as well as data at rest. Now, this specific session is specifically about geospatial analytics and fleet monitoring. There are a large number of scenario possibilities that can be unlocked using what we'll talk to you all about. Some of these include scenarios for geofencing, scenarios for ride sharing, scenarios for connected car, scenarios for asset tracking, fleet management, connected manufacturing, race car telemetry. The possibilities are limitless. For the purposes of today and this specific session, we will get into a very specific fleet monitoring example. Now, I'm sure most folks watching like or would have liked ice cream at some given point in time. So we are going to go back to our childhoods and visualize ice cream trucks. Now, in this specific demo, we'll show you ice cream trucks whose locations are sent to Azure, and we're asking questions on the locations of these trucks as the data is streaming in. And the answers are obtained and displayed on a canvas in near real time. Correspondingly, we will also be capturing this data in a data store and asking questions while that data is at rest, thereby unlocking powerful insights on a much larger corpus of data. So let's get kicked off with the demo. All right, so let's kick off a demo for the purposes of which we are going to replay data that we gathered, and this is data of ice cream trucks that were traveling around the country, and we're going to stream them into Azure as if this was happening as we speak. So what you see on your screen is a bunch of data that represents the physical locations of these trucks that are actually moving. Now, I have a fun visualization for you where I'm showing you these trucks overlaid on a Bing map. Just to show that these trucks are actually moving, I'm going to zoom in into one specific truck somewhere in Southern California. This is truck number 6, and I'm keeping my fingers crossed that you'll see it move. I just saw it move by one step, and if we give it some more time, it'll continue to keep moving. So this is data that is streaming in as we speak. So on this map, what I'm doing is I'm taking advantage of a service that we call Azure Stream Analytics that enables me to ask questions on this data in motion using a SQL-like query language. So I have multiple toggle switches here, and when I say show me all trucks, what's happening is that this is my Azure Stream Analytics job, the thing that you see on your screen here, which is essentially displaying all of the data from all of the trucks that are coming in, and it's being outputted onto this Bing map. Similarly, I can ask another interesting question. I can choose to know which of my trucks in my fleet are in the state of Colorado. Now, I have to admit I chose the state of Colorado because the geofences for Colorado are particularly easy to model compared to other states that have jagged lines. So, as you noticed here, I was able to click on this toggle switch in my UI, which kicked off the Azure Stream Analytics query that helps me detect the query that I'm going to select right now is the query that's running. And this is the query that helps identify the locations of trucks that are within the boundaries of Colorado. And one of the things that you might have noticed is that the answers show up really quickly in near real time. And that is a large part of the value proposition here. What I'm also going to do is join multiple streams of data. I have the locations of trucks coming in, and I will join and augment them with weather information that I'm pulling from the internet to be able to ask questions like, show me trucks that are in my fleet that are in states where the temperature is lower than a certain threshold. Now, if for a second you can pardon my unit of my choice of temperature unit, you'll notice that here are the trucks that are you could argue are in a safe zone because these are ice cream trucks. We don't want their contents melting. Similarly, I can ask another corresponding question, asking for the trucks that are in warmer states to identify the trucks that are at risk. And if we, give it a moment, we should find that some of these trucks show up. So now I'll switch over to Michael, and Michael will show you all that you can do by asking questions on this data set when things are at rest.
Thank you, Sam. Now I'm hungry for an ice cream. So I will be doing the cold path analysis. Basically, what we have done is we have loaded the messages that you saw streaming by on his screen into an Azure Data Lake account. And I'm now using my own Azure Data Lake Analytics account to query that data and do some interesting analytics. And obviously, I want to find out which trucks drive around with melted ice cream, which means not just that they were in a state that has too high of a temperature, but also that they stayed in that state for too long, meaning, let's say, 2 hours or so. So what I do in order to be able to process that is that I'm registering the SQL Server extension libraries that you can download from the feature pack that give me geospatial capability in NewSQL. It's basically two DLLs. The first one is managed C++, C# DLL called Microsoft.SQLServer.types. And then this DLL uses a native component that implements most of the standardized geospatial operations like SD-intersect, SD-contains, etc. And I'm just using here standard NewSQL to register that as an assembly. So in addition, what I also do is I have two data sources that contain information about US states. The first data source that I have is basically one file that contains all the states' polygons in some JSON format. I built my own custom extractor here that parses this and creates specifically a row set that contains the state information, the area, the well-known text representation that I transform out of that GeoJSON encoding, and SQL Server SQL geography type here that so that I can flow it through my uSQL script annotated with a serialization method. So I currently have to expose this as a UDT, and we'll take a look at it in a second on what this wrapper actually does. So now by having this wrapped, I can now move this code basically through, or this object through my code. The second data source is I have a simple CSV file that gives me the state and its average temperature for that state. I have it in Fahrenheit, Celsius, and Kelvin, so if you don't like the Kelvin, you can also use Fahrenheit or Celsius, although I like Kelvin. It's a little bit geeky. And what I do here is I just do a join between these two data sets so that I basically add the temperatures to the geo objects. And then I wrap that all into a user-defined function here, a table-divided function, so I can provide that information. Now, let me quickly show you how I wrapped this data type. So this is my namespace here that contains the custom extractor. And it basically contains here this my UDT wrapper class, very simple. And then I have a generic serialization function here that just allows me to serialize the data type when the row set gets passed between the vertices. If you write your own, you actually have an easier way of adding a formatter, but because I don't own these data types, I basically have to wrap them at this point in time. And then the extractor here, just for good measure, it's basically going against the data and basically just reads it. And then down here somewhere you see I create a new UDT data type that invokes geometry from text, which is basically taking the well-known text and creates the object out of it. Okay, so the information looks a little bit like this. Let me zoom in. So you basically see here the states, the area, the well-known text. I didn't serialize the binary here. That would be hard to read. And then we have like the temperatures here all together. So that's one input data set. The second input data set is the trucks. So remember the JSON capabilities that we have in uSQL? I basically use that samples JSON library. I also use, again, my geospatial library here, so I can take the points and create a point geography data type. And so what I do here is I go over each one of these path files. There's one file per truck, and extract the JSON. And then I do some processing of the JSON with the JSON tuple to kind of drill into the JSON information to create my well-known text statement, and then also my UDT value here inside a uSQL expression. So now I basically have that, both of these information. So now I can do my query. So here is the query that checks for the melted ice creams. So the first thing is, obviously, I get to my hot states, which is, in this case, temperatures of 290 plus. Then I output some intermediate results, so I can look at that if I want to. Then here, this is kind of the core piece here. What I do here is I basically do a cross join between my hot states and my ice cream truck positions, also getting it out of a table-divided function here, where I use the SD contains to do that merging. So very simple expression, looks almost like SQL Server. The only difference is I have to put .value there because I need to get at the actual value that is wrapped by these wrapper types. And then down here, it's just normal uSQL to basically aggregate the states that people were in and also do the duration, so making sure that I'm only looking at the ones that are spending time there for more than 2 hours, and output that. So let's see who is the person. And there are 3 trucks here, 2 in Texas and 1 in Mississippi, that basically has melted the ice cream.
That is unfortunate. But
yes,
it's fantastic that we can find this out.
So now let's hand back to Sam, and he continues with the presentation.
Thank you, Michael. That was fantastic. So what I want to show you folks is an overview of the data flow here that is actualizing the Lambda architecture for you. So on the left-hand side, we have the trucks and GPS sensors on these trucks that are sending data to Azure. Azure Event Hub is the low latency distributed queue, which is an Azure service that receives this location information. And Stream Analytics is the service that I'm using to ask questions on this data that is coming in using a SQL-like query language that I just showed you. In addition, we have reference data, which is static data that doesn't change very frequently, and it's different from streaming data. To augment and join with the streaming data to be able to ask questions. So in this case, data such as the location boundaries of states are things that I'm ingesting from a reference data source. Now, from Stream Analytics, I'm outputting this to a real-time dashboard, a live dashboard. Azure Stream Analytics natively supports integration with Power BI for the purposes of live dashboarding. Concurrently, what I'm also doing is outputting the raw data that Azure Stream Analytics receives that you saw in the event generator to Azure Data Lake Store, where Michael is using Azure Data Lake Analytics to ask questions on that data using this language called USQL. And he's generating results from it. So as you can see, we're asking questions on both data in motion as well as data at rest to unlock unique and differentiated scenarios using a consistent tool set and a consistent environment in Azure. And this is how we operationalize a Lambda architecture that we spoke about. Now, I also want to talk to you about the geospatial functions that are natively available in Azure Stream Analytics. Now, Azure Stream Analytics, as you might be aware, provides a SQL-like query language that enables you to ask questions on data that is streaming in. So we have functions that are very similar to functions that you might be acquainted with in SQL Server in terms of being able to identify points, polygons, line strings, to be able to ask questions such as what is the distance between 2 points, or to check if a point is within a polygon, or if a polygon is within another polygon, or to see if areas overlap, or if lines intersect. So these are capabilities that are natively built into Stream Analytics, and we've standardized on the GeoJSON format for the purposes of asking these questions. I showed you a bunch of examples and scenarios that can be unlocked with Stream Analytics and using geospatial functions for fleet monitoring. On this slide, I'm showing you several other examples. In fact, we have customers and partners in the automotive industry that are using Stream Analytics for powerful connected car and connected truck scenarios. For example, we have a scenario where a car company wants to generate an alert to the driver when the gas levels are lower than a certain threshold and a fuel station or a fuel pump is close by. We can also have scenarios where if a certain number of cars are performing a hazardous braking operation at a specific street intersection, it's possible to alert other cars in the area that are heading towards that intersection about potentially hazardous driving conditions. So these are, again, just a sampler of the several possibilities where you can join and aggregate data from multiple streams using Stream Analytics and use a SQL-like query language with inbuilt geospatial functions to be able to answer questions. The same is the possibilities are equally profound with Data Lake Analytics, and for that I'll transition over to Michael.
Thank you, Sam. So on the Data Lake Analytics side, as you have seen, geospatial processing is not yet part of the USQL offering out of the box, but it's very easy to use the extensibility mechanism that USQL provides to add it to do geospatial processing. You basically use the SQL Server feature pack to do so. You wrap it into a container type, so you can use it inside an extractor and flow it. And then if you want to actually store it inside a table, which I didn't show you for time reason, you can use a binary serialization, such as the well-known binary format, to just put it into a byte array inside your table. And then when you read it, you just rehydrate it as the first step, and then you process on it. Now, one caution that I have is that if you have a lot of data, then your spatial operations might be very expensive. And in SQL Server, obviously, we have geospatial indexing that gives you a lot of performance there. USQL does not have that at the moment. So you will have to build your own approximate tessellation table or something. So you can kind of look up how we implemented that in SQL Server. There's some presentations on that around, I'm sure. And then you can find basically a smaller number of potential matches. So you only have to apply the geospatial operations on this candidate set to then basically do the processing. So it's basically implementing a user-managed spatial index that you would have to do. Now, if you have requirements around geospatial support in USQL beyond this, you will have our contact information at the end. Feel free to contact us and let us know your scenarios about that.
Certainly. Thank you, Michael. Now I want to focus in a little bit on the differentiated value propositions of the services that we spoke about, namely Azure Stream Analytics and Azure Data Lake Analytics. So if we look at these two services, you'll notice that these are serverless entities. These are job services as opposed to cluster services that you might be used to and familiar with. In fact, we offer cluster services on Azure under the name of HD Insight. But these are serverless job services where we optimize for programmer productivity through a declarative language surface. So be it Stream Analytics query language or USQL, the base of it is declarative. And we are fundamentally of the opinion that a declarative mechanism, a declarative language surface will allow for greater programmer productivity while reasoning about data. Now we also have extension mechanisms where you can use C# like primitives and JavaScript for the time being with Stream Analytics to be able to extend beyond the declarative possibilities for these two languages. These are also fully managed services that come with an SLA that ensures 3 nines of availability at the very least. And the other interesting point here is that by virtue of this being a job service, it's fully managed for you. So details associated with the internals of the cluster and some of the low-level details that you might have to deal with if you're using a cluster service are abstracted out from you. And this is also true for scaling some of these entities. The inbuilt integrations that come with Stream Analytics and Data Lake Analytics with Data Lake Store, as well as a whole number of other Azure services. We just showed you integrations with Event Hub and live dashboards, essentially enable the ability to get started with these services using a few clicks of the mouse without necessarily having to roll out your own adapters to connect these several services. Lastly, we've told you all about the service and we've showed you a use case. We want to challenge you by asking you what apps could you develop if you could predict, detect, and adapt to live data instantaneously. And for that, if you need our assistance, we're always here for you. We from the engineering teams offer to provide education as well as assist with the direct build out of solutions and platforms that you might be looking to actualize using some of the services that we went over, in addition to jointly marketing it with Microsoft. Again, if you have any feature requests or if you'd like to engage and partner with us, don't hesitate to reach out to us directly. On the screen, you'll notice our email addresses as well as our Twitter handles. And we look forward to engaging with you.